Okay, hey again, AP Chemistry. So this video, I will talk about how we could use a given equilibrium constant, an initial concentration, and an dissociation equation, or just a chemical reaction in equilibrium, to figure out my equilibrium concentrations. So remember, my Kc in this case is going to be given to me, and my Kc expression is going to be equal to products over reactants. So it's concentration of H plus, concentration of C2H3O2 minus, all over the concentration of HC2H3O2. I'm trying to figure out all of my equilibrium concentrations. On your entrance task, I just want to know one equilibrium concentration, but I'm going to show you how I can get all of them. And the best way to do this, of course, is with an ICE table. So I'm going to rewrite my chemical reaction, H3O2 aqueous, in equilibrium with H plus aqueous, plus C2H3O2 minus aqueous. And here's my construction of the ICE table. So ICE. And it's really important that you learn to love these ICE tables for these type of reactions, especially acid-base chemistry, because in showing your work in this way, it helps the AP graders understand what you were doing and where your mess up was. And so if you mess up in a calculation here, then you could carry on these calculations in the next steps and it'll be fine. If they don't know where you got your numbers from, that's a problem. Okay? Alright, so I'm hoping by now you are familiar with ICE tables, and if not, I posted another video on how we construct and use ICE tables, and I'm going to try and fill it in. Well, I have an initial concentration, and this is just given to me. I have an initial concentration of acetic acid, which is 2.5 molar. So I'm going to put that in my I. This is my initial. And I know, initially, I'll have 0 H plus and 0 C2H3O2 minus. Okay? Now, I do not know my equilibrium concentrations. I do not know my changes yet. So what we do is use X as a variable that we're trying to find. I know as a reactant, I'm losing some molar quantity, and everything is 1-to-1 mole ratio. So I'm going to lose an X. This goes in my change. And whatever I'm losing here, since my H plus and C2H3O2 minus is a 1-to-1 mole ratio, I'm going to get plus X plus X. So at equilibrium, it's going to be my 2.5 molar minus X, X, and X. We've done this before, except I've given you the value of X, and then you've plugged it into my change, and then figured out my Ka. Now, or Kc. Now I've given you the Kc. It's 1.8 times 10 to the minus fifth. So I'm going to plug in this equilibrium section into my K expression. I'm going to substitute in my concentration of H plus for X. I'm going to substitute my concentration of C2H3O2 minus for X. I'm going to substitute my concentration of HC2H3O2 for 2.5 minus X. And I already know my Kc. So Kc is equal to concentration of H plus, concentration of C2H3O2 minus, over the concentration of HC2H3O2. And now I'm just going to plug in my values. 1.8 times 10 to the minus fifth is equal to X, X, all over 2.5 minus X. Okay? Now, some of you, as you were showing me your work, you did this whole quadratic business, which you end up getting about the same answer, but I want to show you a lovely shortcut, and the AP exam is fine, but you need to explain why you do this shortcut. Now, I'm going to eliminate this minus X. Since Kc is small, X is small, negligible, to subtract. So that means if x is small, let's say I had 2.5 minus 0.000001. If I plug it into the calculator, I'll get 2.499999999, which is basically 2.5. So this subtraction of x can be eliminated. And so I could so this is just a tip and a shortcut. So I could rewrite this now as concentration of x all over 2.5. And that's equal to 1.8 times 10 to the minus fifth. On the next page, I'm going to solve for x now. So I had concentration of x all over 2.5 equals 1.8 times 10 to the minus fifth. I'm going to solve for x. So I could multiply both sides by 2.5. So I'll have x equals 1.8 times 10 to the minus fifth times 2.5. I'm just doing algebra now. X times x is x squared equals, if I do 1.8 times 10 raised to the minus fifth times 2.5, I get 4.5 times 10 to the minus fifth. Okay? And now, to solve for x, I just take the square root of both sides. The inverse function of x squared is x. That's how I isolate x. And so x is going to be equal to 0.0067, and I'm going to leave it at that. And this is my concentration. So if I go back to my ice table that I had here, I'm going to reconstruct the ice table. To get my equilibrium concentrations, I'm just going to plug in my value of x. So if I were to reconstruct that ice table, I'm doing it on a separate sheet of paper, but you could just go back to yours. H plus aqueous plus C2H3O2 minus aqueous. I had 0, 0 plus x, and that x is now equal to 0.0067, 0.0067 molar. 2.5 molar was my initial change equilibrium. So this becomes 2.5 minus x, which is equal to 2.5 minus 0.0067. I'm sorry, I forgot the 0. I'm just plugging my values in. So now I know that my equilibrium concentration of H plus is 0.0067, 0.0067, and my equilibrium concentration of my acetic acid, or HC2H3O2, is 2.4933. That's not the right sig figs, but I'm going to show you that just so you know that this basically rounds to 2.5. And so these will be my equilibrium concentrations of any of my reactants and products using the Ka. And you could check your work by plugging these values in to see if I get the Kc as I did before. So Kc should be concentration of H plus, concentration of C2H3O2 minus, all over the concentration of HC2H3O2. If I plug in these values, 0.0067, all over 2.4933, I get 67 times 0.0067, and I divide by 2.4933, I get 1.8 times 10 to the minus fifth, which is my Kc that I had earlier. Okay, so this is how we use a given Kc value and an initial concentration to solve for equilibrium concentrations. So please, if you have any questions or concerns about how we do this, let me know. I would suggest rewatching this video slowly or rewinding if you need to, because I really covered everything that you need to know for things that you will see on the AP Chemistry exam regarding this question.